Okay, we're going to get started. I'd like to welcome everyone here tonight. My name is Miss Wiebe, and on behalf of the Science Department, I would like to welcome parents, students, administration, and school committee members to Stoughton High School's 59th Annual Science Fair. The Science Fair is a unique opportunity for us to celebrate the accomplishments of so many of our students. This year, over 250 students participated in the Science Fair with 29 traditional projects. This night takes a lot of preparation, and I would like to thank the students for their hard work and the science faculty for their dedication over the past months. Staff mentored students as they researched their independent projects and built their engineering models. In addition, most of the science department is here with me tonight to facilitate the competitions. This event would not be possible without them. I would also like to thank all the judges who are here this afternoon to judge our traditional projects. Earlier this month, a cover contest for the Science Fair booklet occurred, and we had over 50 submissions. The faculty voted, and the winner of the cover design was Cameron Smith. And now I'm going to start with tonight's awards. I'm going to ask those students who are called to come up to receive their award and to stay until all individuals in that event have gotten their awards. We'll take a picture as a group for that particular event. Downstairs in D105, you may have seen the safety posters on display. The objective of this event was to design a poster showcasing one of the laboratory safety rules or procedures. Third place in this event was Shauna Laguerre. Second place, Desiree Bulliard. I have the same. First place, I have the same name.
Shauna Laguerre.
Shauna Laguerre. Also in the same room on display was a new project, Safety Infographics. The objective of this event was to design an infographic showcasing one of the laboratory safety rules or procedures using computer software. Third place in this category is Kamari Keith. Second place, Jillian Kimball. And first place, Emma McSweeney. So these posters and infographics were submitted in September, so they were months ago that the students designed those. In the wind turbine event competition, the objective was to design and construct a propeller system which generates the greatest voltage. Third place in this event was Dia Patel and Caitlin Holmes. Are they here? Second place, Allison Flewing and Alana McCormick. First place, Christina Brashara and Raksha Pakarao. Oh, there we go. No one else went up before us, so no. In the engineering event Mousetrap Vehicle, students design and construct a vehicle that uses one or two snap mousetraps as the sole propulsion energy source. The vehicle must travel a specified distance and then return to the starting line as quickly as possible. Third place in this event, Greg Furman. Second place, Vlad Vasilet. First place, Jack Brown. I'm going to ask Molly Cochran, member of the school committee, to come and announce the next awards.
Thank you. In the event micromole rockets, the objective is to optimize the fuel mixture for a miniature rocket and launch it so that it is propelled furthest across the room. Third place in this event goes to Cynthia Gulcharan and John Ortiz. Did I totally mess it up?
Oh, I messed that up. Sorry. Say Carter Jerome. It's messed up. Cynthia and Carter Jerome. Can you say that again?
Okay, so I'm sorry. Third place, there's a correction. It's Cynthia and Carter Jerome. You waited for me to go there. All right. Second place is Tess Billow and Allie Howe. Congratulations. And the first place award goes to Brian Peoples and John Ortiz. There's a name here. I'm not going to be able to say it on the next page. Checklist. Just called SoQuest. Ignore the G. Okay, thank you. All right. And next, in the event Collaborating Towers, held here in this room, students previously built balsa wood towers. The objective of the event was to have the greatest ratio of weight held to weight of the structure. In third place, the award goes to Lauren Bertoletti and Lucian Sarkis. The second place award goes to Nate Bodette and Sana Seth. And the first place award goes to Alex Soquist, Paul Feeney, and Ryan Delinsky. Congratulations. And now in the robotics event, Clean Sweep, also held here in the gym, teams compete head-to-head using robots designed by the teams to move footballs and small soccer balls across the barrier. Each football is worth 5 points and the small balls are worth 2 points. The team in third place is Ryan Struck, Jeremy Fishman, and Dakota Daxberger. The second place award goes to Sophie Timarkian, Justin Kelleher, Frankie Gilmore, and Cameron Bean. And the first place award goes to Alex Gerasitis, Gio Marquez, Tyler Cassidy, and Jared DeRosa. Congratulations. And now to introduce our next awards, our principal, Juliet Miller.
Good evening. Could we just take one moment to recognize Miss Amy Weeby, who put together the science fair this year for the first time? Big round of applause. It is truly a monumental task, and she made it look pretty easy, so nice job. And now for our traditional projects. The traditional projects fall into two groups, individual and team. In each division, projects are judged for creativity, advancement in science, originality, thoroughness, and scientific approach. The highest scoring project will automatically be eligible to compete in the Massachusetts State Science Fair. Several of the highest scoring projects will be eligible to represent Stoughton High School at the South Shore Regional Science Fair. Before I announce the winners, I would like to ask all students who win an award for a traditional project, team, or individual to stay for pictures and information after the event has ended. For team projects, third place is awarded to Bhumi Patel and Caitlin Young, creating an artificial pancreas. Second place is awarded to Lisa Romanowskis and Amanda McGillicuddy. Excuse me. Their project was titled Vitamin C Titration of Fresh, Canned, and Frozen Foods. First place is awarded to Stevens Bontemps and Connor Cavanaugh. and their project was titled The Glowing Transformation Efficiency in E. coli. And now I'd like to call to the podium Superintendent of Schools, Dr. Marguerite Rizzi.
So I will now announce the individual awards. Honorable mention is awarded to Leandra Andrade for the project, The Effects of Microwave Radiation and Heat on Life. Additional honorable mention goes to David Salucci for the project Hydrogen, the New Fuel. Third place is awarded to Colin Cochran for the project Y-Tunes, a study in the evolution of popular music. He's at a track meet right now, so we'll save his award for him. Second place is awarded to Julia Awad, and the project is What is More Superior, Wind versus Ocean? Awesome project. And first place is awarded to Jonathan Podesta for the project Extending the Range of Electric Cars with Bladeless Turbines. Thank you all for coming and have a great night.
Okay, so my name's Connor Kavanagh, and this is Stevens Bontemps, and our project was called Giving Jellyfish Genes to Bacteria. And so our hypothesis basically was if we take the plasmid from a jellyfish, so the DNA from a jellyfish, and insert it into E. coli, which is a bacteria, at a certain temperature for different amounts of time, how that would affect how well that DNA is transferred. And the results of that were if the plasmid was successfully transferred to the bacteria, then it would grow on plates with ampicillin on it, which is an antibiotic. And it would also glow in the presence of a certain sugar called a ribinose.
All right. So for gene expression, in eukaryotes, like animals, similar to like jellyfish, they only use only about 3% of the DNA in their cells. So basically, the DNA has to go through a process in which during protein synthesis, it is taken out and it undergoes a process of alternate RNA splicing, which takes out the DNA that is not used, which is called exons. Then the edited mRNA is then taken and then exposed to reverse transcriptase, which is an enzyme that takes that mRNA and turns it back into DNA. That DNA is then taken and then placed into a plasmid, which is a circle of DNA that bacteria can use. Then, the plasmid is cut open using restriction enzymes, and then the new DNA strand is placed in, and then it is they are binded together using another enzyme called ligase, and then they are annealed together to help the two new strands bind together. And then after that, you have a new plasmid that contains the new DNA of the wanted genes. And in prokaryotes, different from eukaryotes, prokaryotes use all of the DNA in their cells. So they don't have like the alternative RNA splicing to get rid of the exons. That's why it needed to be done before while it was still in the eukaryotic cell. And the DNA in a bacterial cell is contained on groups of genes called operons. There are different types of operons. In this case, we used a inducible operon, which is basically it is always off unless it is induced by an inducer molecule, which in this case is the sugar called arabinose, which turns on the gene, and then the gene turns on the first gene, and then the rest of the genes on that operon can be read and transcripted and translated to later form proteins. In our project, we have 3 genes on our operon: the ARA-C gene, an ampicillin-resistant gene, and the GFP gene, or the green fluorescent protein gene. So yeah.
And the result of our experiment was that the plasmid was successfully inserted into the E. coli. So we had growth on the plates with ampicillin on them, that the P-glow plasmid was inserted into the E. coli. And the E. coli with the plasmid also glowed in the presence of the sugar arabinose that Stevens just talked about. But it worked better at the 50-second time in the hot water bath rather than the 60-second time in the hot water bath, which sort of confirmed the idea that the plasmid could be successfully inserted into the bacteria, but needed the 50 seconds rather than the longer extended period of time. And this can be applied to future uses, such as currently biologists are helping fight diabetes with this by inserting human-made, DNA for human-created insulin into bacteria and growing that, and then harvesting that insulin to use to fight diabetes. And for Alzheimer's, amyloid plaques build up around the neurons and sort of get in the way of them communicating, which causes Alzheimer's disease. And if they can successfully insert DNA, that would attack those plaques, and that would help sort of fight Alzheimer's and the effect that Alzheimer's has on the brain.
Hi, I'm Jonathan Podesta. This is my project, Can a Tesla Turbine Power a Car Using Nothing But Air? This was a continuation project conducted between last year and this year. Last year I tested the viability of an invention of Nikola Tesla that's almost a century old, known as a Tesla turbine, which is a bladeless centripetal flow turbine to power a car directly connected to its drivetrain. And the Tesla turbine is powered with compressed air, so there is no emissions and no pollutions. So I tested the turbine at various PSI from the air compressor and measured its rotations per minute, horsepower, and torque outputs. The rotations per minute were quite high. The horsepower was around 64 at the highest PSI I tested, which seemed viable to power a small car. However, the torque value was pretty low. It was just under 4 pound-feet of torque, which led me to my conclusion for last year, which was that the Tesla turbine would not be a viable alternative to an internal combustion engine for direct power to an automobile, because this torque would not be enough to overcome the static friction of the wheels on an automobile. However, I recognized that the high RPM rates could be very useful in a regenerative battery system, and I talked about this in my future applications last year. I took this system, this idea, and went with it this year for my project, extending the range of electric cars with bladeless turbines. So the problem that I faced was the immense amount of pollution that internal combustion engines release into the atmosphere and the relative impracticality of electric cars due to their short range. So my hypothesis was if a Tesla turbine, as seen here, is attached to an alternator right here, the electricity produced by the system will be enough to recharge the batteries and extend the range. So here I have a 62 amp alternator, and I ran the Tesla turbine at about 16 psi to achieve 10,000 RPM here and 6,000 RPM here, which put out the maximum rating of 62 amps from the alternator. This electricity, I then calculated how that would recharge the battery pack on a Tesla Model S automobile. There are 6,800 individual battery cells in a Tesla Model S battery pack. It turns out that these 62 amps that this alternator produced are pretty low, and it would only extend the range if you were driving with the system running for, say, an hour by 0.073 miles, which is essentially nothing. And I was ready to wrap up the project there, but then I came across something on Tesla's website which I found very interesting, which was that the charger that Tesla sells with the Model S is rated at 10 kilowatts. This alternator is rated at 0.7 kilowatts, so almost 14 times less power. So I wondered if I replaced this low-powered alternator with a generator that ran the same way from the belt-driven Tesla turbine, would it be able to actually mimic the charger of the Tesla turbine and recharge these batteries? So sadly, I was unable to purchase one of these because they cost upwards of $900, but they provide very specific specifications online, and I was able to use the statistics from their website to interpolate and create data. So my system here, this shows a Tesla Model S. There would be an onboard air compressor, 40-gallon air tank, which would then feed air to the Tesla turbine, which would rotate and turn the 10-kilowatt generator's axle, which in turn would produce electricity, which would go back to the batteries to assist in recharging. So with this system in place, if you drove for 8 hours with an average speed of 37.5 miles per hour on a normal Tesla Model S, you would get 300 miles of range. With this system, this regenerative battery system, that 300 miles has now increased to 510.57 miles. And now instead of being able to drive for 8 hours, you can drive for 13 and a half. The extended range is greater at lower speeds because less electricity is being used by the Tesla turbine. I looked at some crash statistics when designing this here to make sure that it was safe, and I noticed less accidents occur in the front of a car at speeds greater than 30 miles an hour than in the rear, so I put the air tank at the front. And the thing about this design that makes it innovative is there have been regenerative battery systems in electric cars. However, they have all been driven with an internal combustion engine which runs on gas and pollutes. And it seems kind of counterintuitive to me to buy an electric car for the purpose of not polluting and then realizing, oh, I don't have enough range in my car to get where I want to go, so let me put a combustion engine in there that pollutes. It just kind of negates the purpose. So this is, at least as far as I've been able to tell based on my research, the first regenerative battery system on an electric car that does not produce any pollution or use any fossil fuels. Its only fuel is compressed air, and its exhaust is regular air. So this system, when in place with the 10-kilowatt generator and the Tesla turbine, will extend the range of a Tesla Model S up to 70%. And future applications, this could definitely be a viable source of rechargeability in any electric car, not even just a Tesla Model S. But the more range you get out of your car per drive, the less you have to charge it, and the less energy is coming from coal-burning power plants, which contribute to the pollution problem that we're facing currently. So this system, I definitely see a future based off of this system, and I see a future for the Tesla turbine and bladeless turbines alike. And that's basically my project as of right now, but I plan to continue with it.